Hey everyone, welcome back to the channel Code with AKJ. Today is day 17 of solving LeetCode 75 challenge, and today's problem is longest subarray of ones after deleting one element, and this is the final problem in sliding window technique. So let's get to the problem statement. Given a binary array nums, you should delete one element from it. Return the size of the longest non-empty subarray containing only ones in the resulting array, and return 0 if there is no such subarray. So today we are solving an exciting problem from the LeetCode, longest subarray of ones after deleting one element. We'll explore both the brute force and the optimal solutions, and we'll break them down step by step. So if you are preparing for coding interviews, so you don't want to miss this one. So let's dive in. So the problem statement here says you are given a binary array nums and you can delete exactly one element from it. The goal is to return the size of the longest subarray of ones in this resulting array, and if there's no such subarray, we'll return 0. So given example here nums 1101, and we need to delete a number in this given array such that we'll get a subarray containing ones, and we need to return that longest subarray containing ones. So in this given example, if we delete 0 from this given array, we'll get a longest subarray containing ones, that is 3. And given in example 2, if we try to delete this second 0 from this given array, we'll get a longest subarray containing ones, and the length of that longest subarray would be 5. So in the given example 3, we already have a longest subarray containing ones, but we need to perform this given operation. So we'll try to delete one element, getting our subarray the length 2. So in this given example 3, we'll get the length of the longest subarray containing ones as 2. So let's get started with our brute force approach. In our brute force approach, we'll simulate deleting each element one by one, and we'll calculate the longest subarray containing ones each time, and we'll repeat this process for every possible deletion, and we'll keep track of the maximum length. So let's quickly analyze our brute force approach by taking these two examples. So these are the two example binary array nums. So if we try to delete each and every element from this given array, we'll be left out with these subarrays. That is, if we delete the first element, we'll get a subarray 101, which contains the maximum longest subarray containing ones as 1. And if we delete the second element 1, we'll get the subarray 101, which also contains the longest subarray containing ones as 1. And in the same way, if we try to delete 0, we'll get a subarray 111, which contains the subarray of continuous ones as 3. And finally, if we try to delete the last element of this given array, we'll get the subarray as 110, which has the longest subarray of containing 1 is 2. So in this given first example, our answer would be 3. Coming to the second example, these are the few subarrays if after we delete one element. So if we try to delete this 0 from this given array, we'll get a subarray as 0, 111, 1101. And in this given subarray, we have a subarray containing ones, and it has the length of 5. So in this given second example, we'll return a value 5. So this was our brute force approach. The time complexity of this approach would be O of n square, as we are trying to delete each and every element and try to check the longest subarray containing ones after deleting each and every element from this given array, and the space complexity here would be O of 1. So let's quickly write this code and let's submit. So here's the brute force approach code. Here the algorithm says here that we iterate through each index I in the given array, and we'll temporarily skip the element at index I and count the length of the longest subarray of ones in the remaining array, and we'll update the maximum length and we'll return the maximum length after finishing these two loops. So let's quickly go through each and every line of this given code. I have taken the size of a nums array. I have taken the max length, which would be initially 0. We'll use two for loops, and we'll try to calculate the current max number of ones we found in that particular subarray. We'll skip each and every element for each loop. So if j equals I, we'll continue that. That means we skip that current element for this given iteration. And for that particular subarray, if nums of j is equals to 1, we'll increment our current max length and we'll update our max length. And if not, if we found a 0 in that particular subarray, we'll try to void the current max length. That is, we'll make current max length as 0. So after finishing these two for loops, we'll return our max length. So let's quickly run this code. So let's submit. As you can see, this approach gives us time limit exceeded because of its time complexity, that is O of n square, as we loop over each and every element and calculate the subarray. And the space complexity here is O of 1, that is no extra space used here. So now let's optimize this using the sliding window technique. So instead of removing each element manually, we'll maintain a window that ensures exactly one zero is excluded while tracking the longest subarray of ones. So here are the steps for our optimal approach where we use sliding window technique. So the first step in our algorithm would be to initialize two pointers left and right and a variable zero count, which would be initially zero. This is to track the number of zeros in the current window. So we'll maintain a window where we try to keep only one zero in this particular window. We'll expand this window by moving right and include nums of right. And if the zero count exceeds 1, we'll shrink the window by moving the left pointer until or unless the condition meets. That is, zero count should remain 1. And we'll finally update the length of this window, that is using right minus left plus 1. And finally we'll return our maximum length. And since we need to delete a particular element, so we'll delete minus 1 from our max length. So this would be our algorithm for our optimal approach. So let's quickly code this approach and later on we'll dry run using this given example. So here's the code for the optimal approach. So we have taken left pointer, max length and zero count. We have looped over this nums array using right pointer. So if the nums of right is 0, we'll increment our zero count variable. And we'll also update our max length parallelly by comparing max length with right minus left plus 1, that is the size of our current window. And we'll check the given condition, that is while zero count is greater than 1, we'll try to shrink our window by removing our nums of left by moving our left pointers. That is, if nums of left is 0, we'll decrement our count variable and we'll move our left pointer one step ahead. And finally, since we need to delete one particular element from this given array or this given window, we'll return max length minus 1. So let's quickly run this code. So again, so let's submit. As you can see, this gives us a successful submission. Here the time complexity for this approach would be O of n, as each element is processed once, and space complexity is O of 1, as we have not used any extra space. So let's quickly dry run this optimal approach using example, and then finally we'll analyze the time complexity and space complexity of both the approaches we have discussed. So let's dry run with this given example. So we'll start with a left pointer, that is 0, max length which would be 0 initially, and zero count which would be 0. So here the right pointer would start from index 0, since nums of 0 is 0. Our current window contains 0, and since nums of right is equals to 0, we'll increment our zero count from 0 to 1. We'll update our max length using right minus left plus 1, that is 0 minus 0 plus 1. So it gets updated from 0 to 1 as well. So coming to the second iteration, we'll move our right pointer to the next index. Here nums of 1 is 1. So our current window contains 0 comma 1. And since nums of right is 1, the 0 count remains same. We'll update our max length, which would be right minus left plus 1, that is 1 minus 0 plus 1. So it updates from 1 to 2. And coming to the next iteration, since the nums of right is 1, 0 count remains same. Our window contains 0, 1, 1. And we'll update our max length from 2 to 3. Coming to the next iteration, since nums of right is 1 as well, we'll include it in our current window, that is 0, 1, 1, 1. We'll update our max length from 3 to 4. And next iteration, since nums of right is 0, we'll increment our 0 count from 1 to 2. So here the condition violates. So we'll try to shrink this given window from the left side. So here the nums of left is 0, so we'll remove it. So our current window contains 1, 1, 1 and 0, and 0 count changes from 2 to 1. Again, for the next index, since nums of right is 1, we'll include it in our window. Here the size changes, so we'll update our max length from 4 to 5. Again, for the next iteration, the nums of right is 1. We'll include that in our window and we'll update our max length from 5 to 6. And for the next iteration, the nums of right is 0 and the 0 count becomes from 1 to 2. Here the condition again violates. So we'll try to shrink our window until or unless our 0 count becomes 1. So the left pointer moves from this point to this point. So our current window contains 1, 1 and 0. So here the current window size is 3, so max length remains same, that is 6. So for the final iteration, the nums of right is 1, so we'll include that in our window, which gives us 1, 1, 0 and 1. Here the current window size is 4 and max length is 6, so the max length remains same. And finally the right pointer moves out of the array and will stop our iteration and we'll get our max length, that is 6. And since we need to delete one element from the given current window, we'll deduct that value from our maximum length, that is 6 minus 1, that is 5. So for this given example, our answer would be 5. So this was the dry run of our optimal approach where we have used sliding window technique, and the time complexity of this approach would be O of n and space complexity of this approach would be O of 1. So let's quickly analyze the time complexity and space complexity of both the approaches we have discussed so far. So for the brute force approach, where we have used 2 for loops to calculate the subarrays, it took O of n squared time complexity and O of 1 space complexity. And for the optimal approach, where we have used sliding window technique, it took O of n time complexity and O of 1 time complexity. And that's how you solve longest subarray of 1's after deleting one element using both brute force and optimal approach. So if you found this video helpful, don't forget to like, subscribe and share it with your fellow coders. I'll see you in the next one. Thank you.